Okay, so the first question is, what is a linear ODE? Well, a linear ODE has a special form, and it's important that you're able to recognise this form. Okay, so the form is just here. All right, it's dy dx plus a function of x times y equals another function of x, where p and q are the functions, respectively, and they're continuous on some interval. Okay, so to give you an example, let's say I was looking at this ODE here. This is a linear ordinary differential equation. Here p of x would be 2x and q of x would be x squared. Okay, let's look at another equation. Dy dx minus 1 on x times y equals cos x. So let's compare this with this, and we would see that p of x is minus 1 on x, and q of x would be cos x. Okay, so that's linear also. Okay, so let's look at something that's not linear. Okay, this ordinary differential equation here has a square root y, not a y in the second term. So this is not linear. Okay, or we usually refer to this as non-linear. Okay. Now, another one that's not linear is something like the following. Okay, here we don't have y, we have y squared. So this is non-linear. Okay, so it's important that you can clearly identify when you are given a linear ODE. Okay, so how do we solve it? Well, I'm actually going to solve a specific example for you now, and we'll talk a slightly in a more general context later. So let's consider the following linear ordinary differential equation. Okay, now if you look at this ODE, it's not separable. Okay, so we can't do what we did in the previous videos and just separate the variables and integrate. This isn't going to work in this side, in this particular example. So how do we actually solve this problem? All right, so I'm going to label this, and I'm going to multiply both sides of our ODE by e to the 3x. Now, you may think, well, why e to the 3x? Why not something else? And why are we multiplying by that thing anyway? Well, just bear with me and we'll see where it comes from and why it's useful. All right, so if I multiply both sides by e to the 3x, we're going to obtain something like this. Now over here I will get e to the 2x. Now, this is an important equation. Okay, if you look closely, the left-hand side is just the derivative of a particular product of functions. Okay? I mean, you look here, you have a y and a dy dx, so a function and its derivative, a function and its derivative. And there's multiplication and addition going on. So can you reduce this to the product of two functions? Well, the answer is yes. The underlined terms are the derivative of the following product. Okay, it's going to be y times e to the 3x. Okay, right, if you differentiate this product, remember y is a function of x, via the product rule, you'll get this. Okay, so what we're going to do is basically collapse this left-hand side down to the derivative of this. And then what I can do is actually integrate both sides. So double star. Double star will become okay, now this is also a very important step. See that we have reduced the analysis down to the derivative of something involving y and x and some function of only x over here. That's important because we can now integrate both sides and get that y out of that derivative in brackets, right? All right, so we're going to integrate both sides with respect to x. Whoops. So on the left-hand side, the d dx is going to disappear. On the right-hand side, I integrate, and I'm going to get a half e to the 2x plus a constant. And, of course, not forgetting the constant of integration. All right, so let's look at this line now. I can rearrange and make y the subject. In other words, I can now rearrange to find the unknown function that satisfies our original differential equation. So if I bring this down here, I'm going to get 1/2 e to the minus x plus c e to the minus 3x. All right, so that's our solution. Now, c is just the constant of integration here. Okay, so let's review that solution. Let's go back and analyse it. The first thing is that we realise that this is a linear ODE. Then I chose this special function, e to the 3x, and multiplied both sides by that e to the 3x. Okay? Then I realised that, okay, I've actually forced the left-hand side to be the derivative of a product involving the unknown function y, and actually this special function here. All right? So I collapsed everything here down to the derivative of a product, namely the unknown function and this particular function here. I integrated both sides and then I rearranged. Okay? Now, a good question here is, well, how did I know how to choose this? Where did this come from? Okay, and essentially, it's got to do with the coefficient of y here, and it's e to the integral of that coefficient. Here it's just 3, so e to the integral would be e to the 3x. Now this has a special name called the integrating factor, and we'll talk about that in a minute. Now the idea works in general, this type of multiplication by this integrating factor. So let's talk about this for a little bit. All right, if I define my integrating factor by this e to the integral p of x, where p of x is the coefficient of y, then the actual solution can be written explicitly in this form 6. Okay? So what you can do is work out the integrating factor, put it in here, and then you've got one integration to do. However, I really don't like that because you're basically just applying a formula here. Okay? What I recommend is the following, is to actually multiply both sides of the equation by the integrating factor and then integrate both sides. It's a little bit more natural. Okay? You're not just applying a formula then. So let's see where this all comes from. Okay, so say I'm given this particular linear, well, this general linear differential equation. I multiply both sides by this integrating factor. And then I realise that this is just the derivative of a product involving the unknown function y and the integrating factor. Okay, so what I can do then is integrate both sides to form this and then rearrange. Now, I may have abused the notation in this justification, but I'm just quickly going through it. Okay, so that's a particular example. Let's look at the next example. Okay, this is slightly more difficult. Okay, now, first of all, we've got our ODE. Here it is. And we've also got the so-called initial conditions. All right? So we know we're given an ODE plus an extra bit of information. We know the value of the unknown function at the point x equals 3. The unknown function has to equal 4 there. All right, so the first thing is that we recognise that our ODE is linear with, okay, so P of x will be 1 on x. And Q of x will be just x. All right, so now let's form our integrating factor. So by definition, our integrating factor, v of x, well, that's just e to the integral p of x. So for this particular example, it's e to the integral 1 on x dx. So we're going to have e to the log absolute x. Now, you can put a constant of integration in there if you want to, but it's not necessary. Okay, if you did put a constant of integration in there and follow everything through, then actually the constant will cancel out later on. But it's not necessary there. Okay, so I don't put it in. Now, we also note that we're really only interested in solutions for positive values of x. So this can be further simplified. E and log cancel, and it's just x because x is positive. Okay? All right, so now what do we do? Well, we take this integrating factor, multiply both sides of our ODE through by it, and then we know that we can collapse everything to the derivative of a product. All right, so multiplication of our original ODE by our integrating factor yields the following. All right, we're going to have x times dy dx plus y equals x squared. Now, if we look closely, this is just the derivative of the product x times y. Thus, what we can do now is integrate both sides and rearrange to produce the solution y. So integration gives the following. So when I integrate here, the d dx is going to disappear. If I integrate here, I'm going to get 1/3 x cubed plus the constant of integration, and now I just rearrange. All right. Now the next question is, can we determine this c, this constant of integration? And the answer is yes, because we can employ the initial condition. Okay, so let's have a look at that. So the initial condition gives the following. What is it? It's 4 equals y at x equals 3. So we substitute x equals 3 in here, and we're going to get 9 on 3 plus c on 3. So if I just solve this now for c, I'll get c equals 3. All right, so what I can do now is go back to my general solution, put in c equals 3, and then I've got my particular solution. One third x squared plus 3x to the minus 1. And note that we're only interested in solutions for positive x. Okay, so I've spent quite a bit of time doing that example just to illustrate all the basic points to you. But you probably wouldn't spend so much time doing it in practice. Okay, you would probably calculate the integrating factor and then probably go straight to this step. Okay? All right. Let's have a look at another example. Okay, solve the following problem. X to y dx plus x plus 1 brackets y equals 2. Now, this isn't in the linear form, but we can rearrange the equation to put it into a linear form. All right, so I'm going to bring that x down here and down here. Okay, so we're going to get y dx plus x plus 1 on x, y equals 2 on x. All right, so this is, and we're only interested in positive values of x here. So this is the actual equation that we're going to work with. Okay, so in this case, p of x is x plus 1 all on x, and q of x is 2 on x. Okay, so let's go through, develop our integrating factor, and then solve. All right, so the integrating factor is the following. Okay, v equals e. It's e to the integral of p of x. So it's e to the integral x plus 1 over x dx. So now we have to integrate this. So if I split that up, it's going to be e to the x plus log absolute x. Now I can simplify this further by firstly noting that I can, well, break this up a bit, and secondly that remembering x is positive here. So if I use my index laws, it's going to be x times e to the x. All right, so I've broken it up and used the fact that x is positive. All right, so let's get down to multiplying everything here by our integrating factor and then collapsing to the derivative of a product on the left-hand side. So Okay, so we multiply both sides here by the integrating factor and then collapse the left-hand side to the derivative of a product. Okay, so right, so let's multiply that by that. We'll get 2e to the x. Okay, you can see now how I've not put in so many steps as the previous problem. So what do we do now? We integrate both sides because you want to get this out of that d dx. So integrating this, I'm going to get 2e to the x plus a constant of integration. So rearrange, bring that over to the other side. I'm going to get 2x to the minus 1 plus cx to the minus 1 e to the minus x. Okay, so I did that one slightly quicker, just to illustrate the main points. Okay, now an important point to note here is that when you're dealing with ODEs, common sense is a very good thing. Okay, in this particular problem, it's not in a linear form at the moment, but you can put it into a linear form. Okay, however, the previous procedures aren't really necessary. You don't really need to build an exponential function for an integrating factor to solve this problem. Hopefully what you can do is realize that the left-hand side is just the derivative of a product. Okay? A really simple product. So, oops. So the left-hand side is just the derivative of, well, it's the derivative of t squared times y. Okay? So what I can do is write this as d dt t squared times y equals cos t, and then integrate both sides, and it will bring out the unknown function, y. So let's call this star. All right, so now I'm in a good situation. I can integrate both sides, and then the solution should pop out. All right, so integrate both sides with respect to t, and I should get something like this. Now, rearrange to form the solution. Okay, so common sense is vital here. I mean, you could, if you wanted to, go through and rearrange this equation and form the integrating factor and then multiply through, but really it's not necessary. It's not necessary because you already have the derivative of this product on the left-hand side. Okay? And to go one step further, if we look at this problem here where the y dash means dy dx, can you see that this is the derivative of a quotient? Okay? Okay, so what's that the derivative of? Well, y on x. So we can solve this equivalent equation to form, okay, integrate both sides, get a constant over here, y equals c times x. Now, of course, you could set the top equal to 0 and solve that way. That's fine as well. But what I'm trying to do is to illustrate how some common sense and some real simple rules from differentiation run backwards can lead to nice solution methods. Okay, well, a couple of questions that I want to leave you with. The first thing is, can I develop this further? Can I develop this further? So, for example, can I get a differential equation down to something like this? I'm not say 0 or something like this. Okay, 0 is just here for convenience. Okay, so can I form some sort of big F that contains the independent variable, the dependent variable, the solution, such that a differential equation will lead to this d dx of this. So I could integrate both sides and then form some sort of implicit solution for y. Okay. Now that's actually the subject of another video called exact differential equations, and that'll be coming up soon. But another interesting question with these linear ODEs, and I'm going to go back to this earlier example. Here I was given a linear ODE and some initial conditions. Now, I came up with the solution way down here. Now, a really good question is that the only solution? Are there other solutions to these linear initial value problems? Well, I'll leave you with those questions, and the next topic will be exact differential equations.